Well, hey there, it's Blast from the Past today. What we have here is a Tektronix TDS210, straight out of 1999. This is one of the much earlier model Tektronix digital oscilloscopes. And I figure what we'll do today is I'm going to take it apart, and it's also going to be a pretty good illustration onto why, for a very long time, DSOs kind of sucked. This is why a lot of people still don't like them, because they haven't used, like the Agilent InfiniVision or any of the deep memory scopes. But fundamentally, basically, the initial DSOs were kind of pretty much shit, mostly because they had an extremely shallow sample memory, like several thousand points, and the sampling time was very narrow. So what would happen is they aliased like a motherfucker, and I'll probably show that in a second. Obviously, you've got two channels. Well, here. So, a couple things to note. One, black and white TN screen. You can kind of see the slow update rate. Obviously, waveforms a second is probably in the order of a couple hundred, maybe. So, they didn't have very good, ratings in terms of waveforms per second. Their update rate was slow. The screen has ghosting issues, just because it's a crappy a TN LCD. So you kind of get the basically the slow LCD effect. So it's actually not terribly unresponsive. I'm actually kind of impressed. I'm not going to recalibrate these scope probes. I mean, you can see, kind of the, oh, that's responsive. So obviously the controls aren't great. You've got just your menu over here. It's actually it doesn't have any of the nice pop-up menus you see nowadays. Obviously, you have your two various. You can kind of see the trace ghosting as I move it up and down fairly rapidly. That's just the slow response rate of the LCD causing that. It's not actually due to any sort of persistence display. Other stuff, none of these are push. If you want to vertically center it, I'm not even sure if there is a way of doing that. Interestingly enough, this was obviously this was a trash pile pull, so it appears somebody used the auto set button a lot, which is kind of funny because I use the auto set button never. So different kind of approaches. Other things if you have two signals, you can't distinguish between them whatsoever. It's very much like good old cathode ray oscilloscope. Those are much more responsive. It kind of makes up for it. So obviously you just have completely binary. But anyways, let's take a look at what I mean when I say ghosting is a big problem with these. So for that, just have. So obviously what we have here is a 1 megahertz sine wave, and the critical thing is if you slow this down, you start getting interesting effects. Like right now, I mean, that looks a lot like a sine wave, but the critical thing is that sine wave right now we're I think we're 25 milliseconds per div. Yeah. So I mean, right now that looks like a let me just stop it. I mean, it looks like a 75 millisecond wave period. So what's happening here is basically we're sampling at a beat frequency. So what's going on is effectively we're seeing, we may be sampling an entire cycle apart, but we're, just a cycle and the tiniest amount. And then what happens is obviously, if you were to view this on a more modern scope, it oversamples enough and it has a deep enough sample buffer that it would still, basically contain the entire waveform, because it would sample, You know, it may be sampling at a gigasample per second, or, you know, 100 megasamples per second, or even 10 megasamples per second. You know, even when your time base is, say, 1 second for the entire window. Whereas with this, you know, if our, like, say my window here is, you know, 1, 2, 3, 4, 5, 10 times 25, so it's 250 milliseconds, and it may only be sampling at 4 kilohertz. So what's going on is each one of those samples is many, many waveforms apart. And the end result is that, just depending on, you know, say, obviously if you sample, like if you have a sine wave, and you sample it, you know, if you have a sine wave with a period of 1 second, and you sample it every second, it's going to look like a DC waveform, because you're going to sample it, and it'll be right at that point, and you're going to sample it, and it'll be right at that point, and you're going to sample it, and it's going to be right at that point, etc. So what happens is, like in this situation, we sample here, and then maybe we sample here a little bit further, so slightly more than one form, and then maybe we sample here, maybe we sample here, you know, and then etc. So over time, you get aliasing, which is simply caused by it sampling at some multiple of an entire cycle. You know, and there's no real way to compensate for that, given the fact that you don't have the depth of memory. So, I mean, I guess one thing they could do, which would have been a much better approach, but they're not doing it, would be to sample very fast and for each point just store the minimum and the maximum. And that would effectively reduce your horizontal memory by half, but it would maintain the envelope. And to be entirely honest, I'm not sure why they ever did that, because obviously this scope is supposed to be 1 gigasample per second. So it's obviously capable of high sample rates continuously without too much trouble. I think mostly just they're competing purely on the points per second, or, you know, or the points per waveform. You know, say, you know, 1,000 points per waveform or whatnot. And I think that's basically they're only looking at that number as the only relevant number when they're effectively measuring, you know, kind of in their dick swinging contest to see who has the better scope. You know, somebody who has 4,000 points waveform memory is better than the guy who has 2,000 points waveform memory, even if the 2,000 points is, you know, complete envelope rather than just, you know, a random point. And the other issue here is obviously that, you know, we're sampling at a gigasample per second, you know, or the ADC is a gigasample per second. So what happens is the actual period of time when it's integrating the waveform input, you know, effectively the period of time when they're actually looking at the waveform input, even when they're sampling at a kilohertz, is very small compared to the actual waveform rate. You know, so it may be the sampling window may not even increase. I'm not sure about that. But in any event, you have you have just horrible aliasing issues. I mean, it does look a little bit like, just from the thickness of the line. Well, I'm not too sure. It looks like they're doing kind of some sort of, you know, slight averaging down, or that could very well just be a function of the screen. Because you can see here, if I, there's no single shot button. But every time I stop it, it kind of goes away. And my assumption there would be that we're simply seeing the response time of the screen forming, you know, kind of forcing it to integrate, which actually is kind of amusing. They're using the fact that the screen is shitty to compensate for the fact that the scope is shitty. But fundamentally, you know, most of the complaints people have about digital oscilloscopes are complaints about scopes like this, where they are, in fact, you know, very valid. You know, I mean, you can actually see here, if I take one sample, it looks like a straight line, despite the fact that, obviously, we have much more dense waveforms. And what's going on here is, you can see, like right now, it's I don't even know where the waveform is. I mean, it looks like we're getting 3 or 4 samples per. I mean, you can start to see some of the structure in the waveform acquisition. So right there is where it starts to go off, kind of off the rails. Whereas at this point, so you can kind of start seeing the intermodulation effects. Like right there is where it starts sampling. So like what we might be seeing here is just actually 2 samples per waveform. I'm not too sure. Unfortunately, this appears to be using like nice. I'm not too sure if it's using like synapse interpolation. Yeah, like there's a very, very low resolution sine wave. You can obviously see we have, you know, low, high, kind of lowish, high, low, high, kind of lowish, high. So we're getting roughly 2.5 to 3 points per cycle at this point. So it does not, I mean, so that's effectively what you're getting when you're, you know, at the very, very low end, you know. And there's kind of another example of it. And then right there is where we're no longer getting a full 2 points per waveform. We may only be getting 1, or, you know, 1.5, which is why it's slightly wide. So in any event, that's basically kind of what anti-aliasing, or what aliasing is when it comes to, you know, sampled systems like this, and why the deep memory of modern scopes is so important. Anyways, I mean, this thing is, I mean, you've more or less seen it. I'm not really going to go into the details of how to use it. One thing that is kind of cute is this has a, this one appears to have a GPIB thing. It's got a Tektronix port, RS-230 port, and GPIB. I actually like GPIB, mostly because, at least at the lab where I work, we have, you know, like a bunch of stuff to talk to with the computers. And if you have the hardware that talks to GPIB, it's actually quite nice. Again, it's kind of, it's one of those, you know, ancient protocols of ancientness that is kind of, there's obviously something that pushes in there. What does it do? I mean, this thing obviously looks like it removes. You can also see, yeah, this was last calibrated in November 1998. Okay, so we've now seen, you know, I've poked around, shown you a little bit about how this works and why kind of the early DSOs were so terrible. Now let's have a look on the inside. Maybe I'll be able to actually get this this GPIB printer module out. Shazam. Alright, well that's interesting. We have some very heavy metallization there. Let's take a closer look at that. So, I mean, that metallization is heavy enough that I almost suspect it's like, it doesn't look like a spray paint, it looks like a vacuum deposition. But that's 0.7 ohms, yeah. And I mean, that's probably mostly, it's significant. A portion of it is the lead resistance. I mean, that's an extremely heavy metallization, and it looks, my assumption is, you know, especially from the way some of these areas here kind of blur out, it looks like, I bet this was vacuum deposited. But in any event, you can also see we have this kind of interesting copper spring assembly down here, which I would assume is just for ground connection. So now it looks like the whole scope just more or less falls out the front. So we have a keyboard membrane. That's interesting. All these are they're all boards branded, amazingly enough. They're like name brand. So it looks like the keyboard. I only see one connector, which is right here, so I think there's probably a... this is a 74HC393, but my assumption would be that there's a decoder or some sort of readout logic on here, which I don't see. The only other thing I see is these two, which are... that's a 74HC405, and that's a 74HC405 as well. So two 74HC405s and one 74HC393. And yet the only interconnects is through this one ribbon down here. That little thin ribbon there, which has 5 pins. So I'm not totally certain. I mean, obviously it's a button matrix of some sort. I'm not sure how exactly that's scanned, but they certainly don't seem to need a lot of pins for it. Oh yeah, of course, take the power switch out. And then, just kind of got to pop over the outlet, and the back is free. So yeah, you can certainly see how, you know, for the number of years they had these in production. That's pretty cool. Look, it's like, it's a flexible braid that it's stiff nevertheless. Focus on my hands. There it goes. It's quite flexible, and yet it's rigid enough that it doesn't collapse very easily. It's springy. But I mean, yeah, look, there's hardly anything in here. You've got your power supply, which is right here. You've got the motherboard. This is for the input, or the control button panel, and then this is to your LCD, and that's it. I mean, these things are very minimal, and yet they charge just hideous amounts of money for them. So it's obviously not too high power. I mean, look at, that's the entire power connection. Looking at the power supply, Dave Jones would be a little scandalized. We've got just free-floating TO220s. That's not free-floating, that actually has PCB tabs. Input, filtering, actually, sorry, filtering's up here. I think that's actually your main rectifier. Oh, this is the CCFL backlight, actually. You can see here. So rectifier right there, bulk bypass, main transformer. Here's your isolation barrier. Looks like it runs, I would assume, up this gap and over. So that's your, this is the secondary side. This whole thing is the primary side. That's probably your controller. It's got 2 optos. I would assume one of these pins probably controls the, I mean, I bet one of these is, because again, the power switch is a hard power switch. I bet one of these is backlight, like PWM modulation for the backlight, and the other one is like feedback for the switch mode supply. What is that device? That's a transistor. We've got, one nice thing is some very nice grounding. I mean, so you can see we've got a big, nice, very strong, heavy, like 12 gauge spade lug. If we know. So you can see here's our cal tabs. It appears this is just held in with 2 snaps. I think these 2 just pop out, and then that's interesting. There's a hole on the back of the case. You see right here. It appears this is a reset button. The problem I'm noticing is just these tabs are going to hit the LCD panel, I think. Let's take the, there's the button assembly. It's nicely even labeled front panel. That's quite cute. So the LCD appears to just have 2 snaps, just like everything else. It's certainly designed to be repaired, if nothing else. So, yeah. It just lifts out, and then I just have to kind of untuck the cable. Like so. So here's just a commercial LCD panel with a plastic sheet on the front. You can see it's got this foam. So that's just, you know, finger guards, so you can kind of point at the screen without having to worry or replace it. But it's very, it feels kind of like a, I don't know what it is, it's a plastic though. And then that's, and that's more or less it. Just barring, however this is supposed to be attached. It definitely appears to tilt up and then slide back. I don't know if you can see, but if we look down in here, there's like registration pins that when this is tilted up sit into the PCB. So, don't see why this won't just slide. Doesn't appear to be caught on anything. There it goes. So, for all intents and purposes, this is the entire oscilloscope. Yeah, Tektronix is certainly being scummy. I mean, when they were just gouging the shit because they were the only people who had these on the market, you know, and they just stopped innovating for like 10 years. And now Rigel and everyone else is just completely kicking the ass. I mean, they're picking up again. But if we look, I mean, fortunately there's a broken one of these I may be able to find, which I can pull off the cover plate. But, I mean, if you look down in there, there's really just, there's that one big chip there, and maybe a couple little relays, like it looks like there's a relay there and a little relay there, which I bet are for the AC coupling, and there's hardly anything in here. And we can see over here we have like the typical layer things. It looks like this may in fact not even have that many layers. Let me change lenses. Alright, so just there's your layer, and it says G on it. So we have E2, EF, and over here we have it, I think this is a 4-layer board, E3, and then it's E back. So it looks like we have, you know, E front, EF, E front, E2, E3, and EB, which I would assume is E back. So this appears to be just a plain old 4-layer board. Backside is mostly empty. There's hardly anything down there aside from passives. We flip over to the front. We have 42S4260. I bet that's RAM. We've got that device there. It's a National Semi MM9527. We have this, which I would assume is the main microprocessor. These were 6800 series based for the longest time. It's an MC68E C000FN8. There's a couple little oddments up here. I bet these are comparators. 74HC453, 4581CS. Not too sure what that is. This is obviously the firmware. It's probably just an EEPROM. This is an AM29F010. That's a PLD if I know my numbers correctly. We've got the clock, which is a 60.606 megahertz. That's kind of an odd frequency. This big connector here is for the rear interface. It's an interesting logo. I wonder who that logo is for. Kind of a split M with a dot in the middle. There's some miscellaneous stuff over here. This is probably like power management and like local power regulation. So this is the connector where the power comes in. So this is all, I bet these are like voltage regulators with the various interesting core voltages. 87CVRFT, you know, whatever. There's a TL431, that's a shunt regulator. Interesting. Here's the ground tab, this is the display interface. And then we just have down in here, so you can see right there is like one of those 6-pin devices, which I think are probably relays. And then there's just the a huge QFP device down there, and that's about it. Like we can look over here and there's almost nothing in there aside from some passives, so I would assume they've got basically that one giant ASIC down there which just does everything in the front end. You know, I guess TI is kind of, that's interesting, it appears to be it's national branded. But I would assume that either, I mean, I guess this could be the ADC and that could be the front end, though that seems kind of unlikely. I would assume that one part there. Yeah, so I mean that's it. There's hardly anything in here. It's an extremely minimal board. Here's the keypad. See the nice, certainly nice quality rotary encoders. They don't have detents, which is a little annoying. I mean, we just got some DIT parts, and then the back of this is just completely Spartan except for heat stake down rotary encoders. It's gold plated, which is kind of nice. The front panel. This one does not appear to be. And then here's the printer, serial, and GPIB interface card. Again, no screws. It's all snapped together. TI certainly does like their snaps. The board just kind of pops out. I bet we'll see some what's that company? National Instruments parts in here, particularly for the GPIB. Got big metal things. Yeah. So we have a National Instruments Q391644 GP18288. That's part of the GPIB PHY. We've got another chip here. I would bet that's for firmware. Got a couple PAL. I bet those are PALs. That's a 68681C1. I think that might be like a 6800 series micros. Again, lots of glue logic. This could be a printer port controller. There's a big, chunky surface mount crystal. Again, this board is entirely single-side load. Got a few things. Here's a Maxim chip. I bet that's an RS-232 interface. Again, this board appears to be 4 layers. And then we have some fairly heavy metal shielding in here, but nothing much here. You can see this is a TDS210 1998, so this is quite old. Kind of from the dark ages of DSOs when they were all kind of shite. Pops back together. And then the only other thing remaining is this, the power supply. So, here's our power supply. There are the two optos. There is the only actual IC on this whole board as far as I can tell, which is a KA7552. So down here, this looks like the backlight transformer. You can see it's got just 2 transistors. It's probably just a very simple oscillator. Some big Y caps bridging the isolation barrier. Well, yeah, they are, I think. You know, obviously there's the primary transformer. This one big transistor on this heatsink appears to be the kind of the power transistor in the whole thing. There's your input filtering. There's the cute little DIP 8 bridge rectifier. various things. That's a little heat shrink resistor. Oh, hey, there's another opto. Some big diodes. There's another transistor. But yeah, no other active devices. But that's a 431. Yep. So that's a programmable shunt regulator, so they're probably using that as the air amplifier. Again, all snaps together. Which means I should be able to unsnap this and we can get a look at the back side. There ain't much there. Actually, let me change on this. So here's the rear side. You can see the isolation gap runs like so. Actually, quite interesting. We have these big capacitors here, and it appears they're in series to bridge the isolation gap. It also seems that the backlight inverters run off the DC supply. Because if you look over here, you see that the DC supply, this is the basically the output section. It runs around this corner over here to the transistors, and then here's the output. You'll also see this is so we have an earth connection here, which goes to that pin there, which goes to that Y cap, which goes over to here. So we have more earth, and then you also see there's actually a provision for another like a Y cap here that's actually not placed. But furthermore, it appears that this lead here actually doesn't connect. It wraps around here, but that is an unpopulated. I mean, yeah, you can see there's it looks like there's an option for a jumper link right here, which would jumper this pin to that pin, but it's not there, which is very strange. I guess maybe that's an option, another earthing option that they'd use if they didn't use the big heavy earthing connection. But yeah, other than that, we've got some very non-trivial input filtering. I mean, it's nicely made. The caps all appear to have some goop, under them, keep them steady. The TO220 device is not great, but whatever. The IEEE connector is nice. It's riveted to the board rather than relying on the PCB tabs. It's just kind of surprising how little output it has. I mean, 2 of these appear to be ground. 2 of them are bussed together, and then we just have 3 other pins. I mean, it's only 7 pins and 5 interconnects. So I mean, it's not drawing very much power. It's kind of interesting, like a contrast to the modern Regal scopes with all the ridiculous interconnects. And the giant motherboard. I mean, just compared to this, which has, basically 2 chips in memory. Okie dokie, so let's plonk it back together. So that's effectively the inside of one of these really old, early generation Tektronix GSOs. These were at the point where the people who kind of claimed that this was the generation where the claim of DSOs basically not even being as good as analog scopes was in fact still very much true. I mean, nowadays I think the Regal and really very much the Agilent and then the Regal kind of as just playing catch up have reached the point where they're as or more usable than like a analog cathode ray oscilloscope. Whereas with something like this, I would, compared to this, if you compare this to like my 7904 or something like that, I'd rather have my 7904. I mean, this is not, the only area where this is even worth bothering with is contexts where you have extremely low rep rates and it's simple to trigger on. Any other situation, analog scope will beat this. Just for the very, the aliasing issues and so many other things. Deep memory, like a digital oscilloscope, that starts to actually beat out like my analog scope in a significant number of areas, and also the fact that it's so much more compact is very nice. Again, like the Tektronix stuff, the Tektronix stuff when Tektronix was relevant, which I guess is happening again, like with some of their newer stuff. Like the old analog Tektronix stuff still has like some of the best analog performance available. And not only that, it's also extremely inexpensive, which is, greatly advantageous. I have, like some amplifiers that'll do, 100 microvolts per division, with great, extremely low noise. And I paid like $20 for them on eBay, So I'd much rather have, something like that than something like this, which goes down to 2 millivolts per division with, horrible granularity and, shitty low update rate black and white screen, and so forth. Just, it's kind of depressing. I mean, you can see, look how much noise that has even. That's 2 millivolt bandwidth limited, and it's got half a division of noise on the input. And actually, noisy. And you can just see the kind of the terrible screen update rate. And it doesn't even have a trigger output, so I can't even tell you how many waveforms a second it's getting. I mean, maybe they offer trigger output as an optional module, but yeah.